just briefly introduce you to our next speaker, Danna Staaf, Ph.D.
So I'm going to take a slightly different tack since we've already heard a lot about how amazing octopuses are, and probably everybody is here because you already think octopuses are amazing. No, octopuses are amazing because you're correct. They are. And I'm going to tell you how they got that way. And this is the incredibly abbreviated history of how the octopus lost its shell, which starts 500 million years ago. And really one of my favorite things about octopuses is that they used to have a shell, and now they're sort of famous for not having any hard parts at all. And so I'm going to show you why it's so important that they used to have a shell, that their ancestors used to have shells, and then also why it's so important that they lost it. So let me see if I can get away with some screen sharing here. Let me just make sure I've got that going for me. Do a slideshow. And then we're going to go here and we're going to go share, window capture, share. Oh, it's going to be amazing. I believe in us. Okay. How are we doing? Can you see this cool drawing of a purple octopus?
Yeah.
Fantastic. Now, this drawing of an octopus is by Sam, of course, as are many of the drawings in this presentation from that really cool collaborative comic that we did about how the octopus lost its shell. So I'm going to jump right into it because I need to make you understand how long ago 500 million years ago is. Now, this is long before there were humans. It is also long before there were dinosaurs. So we're talking like twice as old as the oldest dinosaur here. It was also even before there were any plants on planet Earth. Basically, 500 million years ago, there was nothing on land except maybe some algae, and everything interesting was happening in the ocean. This was the Cambrian explosion. This was the beginning of all of the groups that we think of as modern, not really modern, all of the animal groups that you can think of basically were showing up at this time. And in the ocean, you were getting your first jellies and your first sea stars, and really almost no vertebrates, no animals with backbones like us. Pretty much everything was an invertebrate, no bones. And most of them were also crawling around on the seafloor, maybe burrowing into it. There really wasn't anything that could swim. So it was really like just a seafloor covered with trilobites, worms, and a lot of new predators. So with all of the new evolution of animals going on, they were starting to turn to and eat each other in brand new ways. And that meant that they had to evolve defenses. And so this is when we first see a group called the mollusks, which includes all of our modern octopuses, as well as snails and clams and mussels and squid, of course, and all the other things. They evolved hard shells. And that was their big deal. They had these hard shells that protected them against predators. They could hide inside. And you still see that today in a clam or a snail. It's hiding inside its shell from a predator. And this included all of the ancestors of octopuses. This is also like probably my favorite panel in the whole comic book, so I'm spending a long time on it. It's so charming. It's so good. It's so good. But one of the cool things, so early cephalopods had these shells, and the really key innovation is that once they had a shell, that opened up a new evolutionary door for them. And these early cephalopods separated from all of the other mollusks, all the snails and clams, by using their shell to float. And this was a huge innovation, not just for mollusks, but for animal life generally. Because remember, there's really nothing swimming in the water at this point. And so it's uncharted territory in a sense. And the way it worked for these early cephalopods, once they had that shell, they started to evolve little walls inside it, little chambers. And once it had sealed off chambers, then they were able to actually extract the water, the fluid that was naturally in those chambers, and replace it with gas. So early dirigibles, essentially, early airships. 500 million years before humans came up with the concept. That have these gas-filled shells that are lifting them up off the seafloor. And they literally rose above the competition because there was nothing else doing this. There's no sharks, there's no fish, there's certainly no whales, nothing like that. These guys were the only big swimming animals, and they got really big because once the shell evolved to contain gas, it could offset its weight. Now, a snail that doesn't have any gas in its shell is pretty heavy, so it can only get so big, and it has to crawl around carrying that shell on its back. But a cephalopod that can fill its shell with gas, there's almost no limit to how big that shell can get. And they got huge. These were the first animals on planet Earth that got bigger than we are today. As you can see in these diagrams, there were actually no scuba divers and no business people back in the Cambrian, but we drew them there to make it look like you could see how big these animals were. They were gigantic and they did great for themselves. And then vertebrates came along and spoiled everything. The first fish got big enough to evolve something that could actually damage a shell. The shells were no longer invulnerable because fish had jaws. This was huge. Nothing before this, none of those animals, none of those predators, none of those early cephalopods had a proper jaw. And this idea of something that could open, hinge open, clamp shut with incredible power and break through a shell was a game changer. Cephalopods had to adapt or die. And luckily for all of us who love octopuses, they were in fact able to adapt. And this is when we start to see the beginnings of the ancestors of true octopuses, because I realize none of these cephalopods so far have really looked like octopuses at all. But now we have 3 different groups of cephalopods that are adapting to this situation with the fish and the jaws, and 2 of them evolved coiled shells. As this gentleman is demonstrating for us, when you have something very long, it can get in the way, and one of the natural solutions to that is to coil it up. And when the cephalopods evolved coiled shells, they were able to maneuver more quickly. They were able often to escape fishy predators, as well as compete with them for the same kind of food. And these were the ammonoids and the nautiloids. And we still have nautiluses today. If you've seen the beautiful coiled spiral shell of a chambered nautilus, that is all that we have left today of these groups that were once extremely abundant, and you can still find in fossils all over the world. 2 different groups of coiled cephalopods. And they evolved some pretty weird coiled, uncoiled, spirally shapes to adapt to different niches. Oh yeah, that's great. None of those are the octopuses though, so forget them. The other group that we have that evolved a response to the jaws and the fish was the early coleoids, which is a group of cephalopods that's named for their internal shells. Now, this is not a cephalopod, but it's sort of showing you how it can happen that a mollusk can wrap its body around its shell. This is a type of snail called a cowrie. You may have seen their shells super polished because their mantle, their body, is very often wrapped around it, cleaning, polishing it. And we think that something like this might have happened early in the evolution of the coleoids, because we have fossils like this, where you can actually see the imprint of a soft body on the outside of this crushed seashell. So the white stuff you're seeing in the rock is the shell of the cephalopod, still a very sturdy shell that would have been full of gas on the inside. But then the indentation around it is the soft body that was on the outside. And this was the beginning of the coleoids. This is a reconstruction of what those early ones looked like. Still not super octopus, but we're getting there. We're getting there. And this was incredibly successful for them, because now that they had their soft body on the outside, they could really maneuver. They could really compete with fish in a way that cephalopods had not been able to do it. And this is actually the beginning of what is going to shape cephalopods all the way through modern squid and octopuses, is they're successfully competing with vertebrates. That's us. They are figuring out how to live, in a sense, with an internal skeleton, because that's what happened when they internalized the shell. And so now they're able to swim with this jet propulsion that's more effective when there's an internal shell and not an external shell sort of constricting your body. And they were able to evolve all kinds of other aspects of their body. It's basically all, like, everything that's cool about an octopus is a response to internalizing that shell. So they are able to jet propel themselves more quickly, which led to the evolution of the 3 hearts, which you may have heard of, that fun little fact that cephalopods have 3 hearts. That's to keep the blood pumping, to keep it oxygenated. They have 1 heart on top or below, as it is in this illustration, each of their gills, to get the blood to the gills to pick up the oxygen that it needs. And then a 3rd systemic heart to pump that to the rest of their bodies. All in response to losing the shell. Basically, our modern octopus is this chameleon that evolved from having an internalized shell and then evolution taking it step by step, smaller and smaller and smaller. So one of these pictures is showing how incredible the camouflage of the modern cephalopod is. That's actually a cuttlefish hiding on the sand, looking exactly like the sand, because once your skin's on the outside, you can't protect yourself with that shell anymore. So they evolved camouflage to protect themselves. Same with all of the suction cups on their arms. That was able to evolve once they had this flexible body plan where they could really turn it into any shape that they needed, that the environment. And this is also when you start to see the evolution of the really complex nervous system that, of course, draws our attention to octopuses today in their eyes, in their brains, in their distributed brains throughout all of their arms. And so this is a diagram here showing how distributed that nervous system really is, because they have this complex body with virtually no skeleton that their brain is evolving, their nervous system is evolving to control. And that is pretty much bringing us to the present day, because here we are with the octopuses that lost their shell, and everything that we love about them came out of that evolutionary loss of having a shell. But I did just want to take a moment, since Sam mentioned my comics, to show you a little bit of the, let's call it a contrast in style that we have between the stuff that Sam draws and the stuff that I draw, which I try to make up for with the just extreme nerdiness. So I'm going to stop sharing for just a moment and find one of the recent comics that I feel like really that I made that really illustrates some of the amazing research that scientists are doing on what octopuses are able to do now that they have this complex nervous system and this incredibly flexible body plan. So this is a comic that this is the first of three pieces that I did of this comic about research on octopuses that hunt with fish. So with vertebrates, they've evolved to actually collaborate with their competitors so that both the fish and the octopuses can get more food. And this research that came out recently, the scientists were showing that the octopuses would actually sometimes punch the fish if they felt the fish were freeloading and not sort of pulling their weight in the octopus. In the hunting party that the octopus was leading. So I always like to put some crabs in there as instigators, because I feel like crabs really are instigators. And so then this is the second part.
All the fish are upset.
Fantastic. Yes. Yeah.
There we go.
Very cool. So yeah, I just got an opportunity to also shoehorn in there a little bit of the research about how octopus arms have some independence, right, in their movement. It's not completely centralized the same way ours is, but scientists are still trying to figure out exactly what that means.
The next day.
Right. And then this is the one where I got into their camouflage. And one of the aspects of octopus camouflage that I feel like doesn't get quite as much attention is that they can change the texture of their skin as well as the color and the patterns on it. So that also worked well with my I'm drawing this in pen as fast as I possibly can aesthetic, where I didn't have to do any fancy patterns. I just made the skin all ripply.
Amazing. I love these comics so much.
Thank you. Thank you. I appreciate the opportunity.
I just wanted to quickly share, this is kind of how like Octonation and us work together. We also covered this research here on our blog, Octopuses Punch Fish That Cheat During Hunts, new study. And it's just like, there's so many people that learn in tons of different ways. And we just try to figure out like, how can we make this information more accessible? And like, so the work that you do is so important, you know, and it makes it so much more sticky, I feel like. So thank you for doing what you do.
It's so much fun. Yeah.
Yeah.
Can I answer one of the questions that I just see in the chat, or am I not supposed to jump in?
No, please do that.
Oh my God.
Let me read it aloud. Well, I guess you know which question you want to answer. You just tell us.
I'll read it and then answer it.
Yeah.
Tell me. I love, so I might, because I had to leave and come back to Zoom. I apologize. I might miss some questions, so I'll have Sam jump in there, but I just quickly wanted to answer. Somebody very, very sweetly said, I absolutely loved your short story in the Suction Cup Dreams anthology, which is amazing to me. I love that you read it. That makes me so happy. This was an anthology of all octopus themed fiction, which predates Octonation. I'm pretty sure it's like I can't remember anymore what year it came out, but it was a while ago. But I highly recommend it if you can find. It's probably out of print now. There were a bunch of really bizarre and really delightful stories in there, and I got to write this little story about like a future world in which octopuses had evolved sentience and a like complex tool building culture and language, and I just absolutely loved it. And so the question was, have you written or are you planning to write more about the protagonist's adventures? And I have not written anymore, but I would love to write more. I actually have a number of science fiction stories that involve octopuses to a greater or lesser extent that might one day see the light of day. And I also strongly delight in the idea of laminating the comic and showing it to the octopuses. That would be amazing.
Yeah, +1 rec for Section Cup Dreams. Great anthology. Though, yeah, your story was the best. Maybe I'm biased. Let's do another question. Russ asks, what are like the upsides and downsides, sort of trade-offs of having a skeleton versus an internalized shell?
That is a fantastic question. Just off the top of my head, I feel like one of the basic differences, and the reason that I think probably some people would take issue with me calling the internal shell a skeleton, is that it is not articulated. And that's kind of one of the core things about our own internal skeleton and any vertebrate's internal skeleton, is that we have joints, right? The knee bone's connected to the toe bone, however it is. I'm not a vertebrate biologist, so don't quote me on that. But there's no hinges, there's no joints in an internalized shell, and so you really don't have that flexibility of having different bones that are able to move in different ways, and there's really no joints. So it is limiting really in what can be done with an internal shell like that.
If I recall from the book, it was a speed thing, like not being able to, like having a big shell really reduced the mobility of these early cephalopods.
Totally.
I think when I first met Chelsea, I wrote a piece and I said that octopuses have water skeletons. And I think that was one of the first things she's like, no, not quite. So, but I was like trying to figure out how can I make this, or how can I make it make sense, to somebody else, or like a kid, or just, I think my brother is the one where he's just like, why do you think these are so cool? And so every single time I write, I'm thinking about how can I make somebody, even if they didn't think like they were cool or don't want to talk about it, how could I make them go, you know what, this is pretty cool. You know what I mean? This is neat.
I have a question, Danna. So one of the takeaways from Monarchs of the Sea that I took was that like the cephalopods we have today exist because of these evolutionary pressures and the sort of, for lack of a better word, decisions that were made by evolution before. Like you can't turn back time and evolve something differently. So cephalopods evolutionarily had a shell, and so they had to develop a way to move, and the way that they adapted to that was to get rid of their shell, and thus you have like jet propulsion and other consequences of them having like they have blue blood because their original anatomy used copper to bond with oxygen.
Oh, whoa.
In order to,
if you don't mind me interrupting for a second, there's always like this, what if something else could evolve? For example, I did a bunch of research into, could they ever evolve to use hemoglobin instead of hemocyanin, which is red iron blood instead of blue copper blood? Because there are mollusks that have it. There are other mollusks that have hemoglobin. And the best that I could come up with is it just hasn't happened yet, but there's no like a priori reason why it couldn't happen in the future. So yeah, just like the number of sheer accident, like if it's good enough, then it's there. Yeah, it just kind of reminds you how it's so difficult to avoid talking about kind of directionality and intention when we're talking about evolution, because that's just how we think about causality. We cause things to happen. We want things to happen. But it's funny every now and then to have these reminders of like, no, there's no intelligent force there. It's just what happens. Yeah. Anyway,
Right.
sorry to interrupt you, but the hemoglobin
No.
thing, I was like, wow, that's weird.
Right. So I guess like thinking of like what we have today as this consequence of all of these different evolutionary forces and pressures in the past, if I can ask you to speculate a little bit, like what kind of evolutionary pressures are facing octopuses today, and how might that direct their evolution in the future?
Always a fun thing. I think we're all here for some speculative fiction since we're all here to celebrate Octopolis. I mean, there's so many possible answers, right? But I think that one of the things that you can look at, there's so many different species of octopuses, right? Like Warren has been building this Octopedia, and there's so many species there, and there's still so many left to discover. And the ones that are kind of thriving tend to have shorter lifespans, quick generational turnover, producing lots of babies. And overall, that seems to be a fairly successful strategy in our oceans today, because that producing lots of babies, kind of hedging your bets. Some of them are going to survive, some of them are going to get eaten, some of them are going to die because the environment isn't right for them. That seems to be a really successful strategy, not just for octopuses, but for cephalopods generally. And so I feel like that is an interesting thing looking forward, wondering if that might become even more, like might become even more ephemeral, like many insects that we have today. I don't know. That's the first time I've ever said that idea out loud. So who knows? Every time I think about this, some totally different idea comes into my head.